And hi everyone. And today we will be discussing power series solution of a differential equation. So, as you know, if we have a simple differential equation, we used to express the solution in format of exponential and trigonometric functions. Since most of the cases we get solution with exponential function. Now, say we have a differential equation d square y by dx square minus y equal to 0 is a second order differential equation, right? So you will be having a superposition of the solutions, that is y is equal to a power x plus b power minus x. We can express that solution, that is the exponential and exponential minus x can be expressed in terms of series, right? So here we have a expression that the solutions are expressed in the power series format. Second question we have is the d square y by dx square plus y equal to 0. The solution is given as y is equal to sine x. Obviously, the sine x is also expressed in terms of series, right? So this obtains solution for differential equation series form. The solution of differential equation will be a series of ascending powers of x. Okay, this is true for all the solutions, right? Once you have a solution, right? So the differential equation will be a series of ascending powers of x. Right? I will come to that later. Suppose if we have any equation, right? First of all, we have to find a ordinary point, right? So we have d square y by dx square plus p of x dy by dx plus q y. So whatever may be the general equation, whatever will be the differential equation, we have to rearrange it in this form, right? So then you have to find the ordinary point, right? So I will come to that later. What is going to be ordinary point? In this next example, we will discuss that. Right. So x equal to ordinary point. If the denominators of p and q do not vanish for x equal to, if we have some value at if you substitute that value in the place of x, right? So that term should not vanish, right? So here we have an example here. 1 plus x square d square y by dx square plus dy by dx minus y, right? So uh, here here you can see, here we have 1 minus x square. Just a minute. Yeah, so here we have 1 minus x square, and you can see that we just rearranged this 1 minus x square in the form of x, divided all terms by 1 plus x square, right? So you can find it here, right? So and here we have y minus y by 1 plus x square, right? So then if x is equal to 0, if I put x equal to 0, then p and q should not vanish um, because here y dash is missing here, right? Just a minute. Just a minute. Okay, right. So here dy by dx is missing here. So once you solve this, right? So once you substitute 0, x equal to 0, you will be getting some values, right? And here we have a second problem, right? So we have a second problem here. So in this place, if I put x equal to 0 here, then p and q will go to infinity. So at this point, x equal to 0 is not an ordinary point, and solution for the differential equation when x equal to 0 is an ordinary point. Solution of the differential equation when x equal to 0 is an ordinary, right? So now what we do, now we can express this in the form of a series, right? So we are going to give the series format. That's what we are going to see. I will apply and show you an example for a series solution, right? So for the time being, keep this in mind. X equal to 0 is not an ordinary point. If x equal to 0, at the time where p and q becomes infinite, right? So here we have a solution. It's a general format. Okay, y is equal to a naught plus a1 plus x plus a2 x square plus a3 x. While solving a differential equation, we are able to find the values of a naught, a1, a2, etc. Right? And here the this term can be written simply like this with the help of a summation k equal to 0 to infinity a k x k. Again, these k are dummy indices, right? Once you replace this with k with any other alphabet, you have to replace that here also, right? So right. So now I differentiate this. What happens here? We have to just differentiate with respect to x. So k will come here, and x k minus one. And if I substitute k equal to 0 here, x power minus, it will become x power minus 1. So that is not advisable to have negative powers. So I start this summation with k equal to 1 to infinity, right? So similarly, if I differentiate another terms, right? If I differentiate another time, so I will be getting d square y by dx square, and I have ak k, which is these two terms, and if I am differentiating, I will be getting this k minus 1 here, and k minus 1 will become k minus 2, and the summation will start from k equal to 2 to and goes up to infinity, right? So we have to use these terms in a differential equation, whatever may be the differential equations, since we have whatever may be the coefficients we have for dy by dx, right? So we will be using this terms y dy by dx d square by dx square in the given differential equation. Then you have to calculate a naught, a1, a2, etc. That is the coefficient of various powers of x by equating the coefficients to 0, right? Then we have to substitute the values of a naught, a1, a2 in the differential equation, and we will complete the solution, right? So that will be the solution of a given second order differential equation, right? Here we have a simple example here, right? This is the simple example. You can find it in any books, right? And you can try by your own itself, right? So here you can see that the indices are changed. Instead of k, I used m. So if I use m here, you have to use m here and here also, right? So y dash minus y is equal to 0. It's a simple problem, simple differential equation, first order differential equation, right? So here we have y is equal to, here I am not looking for that ordinary point, singular point. We'll get into that later, right? Once you discuss Frobenius method, we will come to that later, right? So I expressed y is equal to a naught plus a1x plus a2 x square plus etc. And y1 prime is equal to a1 plus 2a2x, right? And because if I differentiate a naught is a constant, that will become 0, and I differentiate a1x will become to a1, and a2x square will become 2a2x. So like that, we are differentiating that. So now we are having y prime minus y equal to 0, right? So y prime, already you know that this is this one, and y is this one. So now we are collecting the same powers, right? So y prime and y prime and y prime minus y, right? So now we are uh, taking the common coefficient. For example, this a1 and a0 are constant, and a2 and a1 have x as a coefficient. Sorry, for x we have 2a2 minus a1, and for x square, for 3 a3 minus and a2 we have x square in common. So once we have this, all these terms are equal to 0. Obviously x is not a 0, will not should not be 0. So we have a1 minus a0 equal to 0 here, and if I equate that, a1 is equal to a0, and then we have 2a2 minus a1. So 2a2 minus a1 is, and we know I just instead of a1 I put a0. So 2a2 equal to a0 by 2. Instead of a1, I am just replacing with the help of this one. I am just replacing this a1 with a0. Then we have a3, 3a3 equal to a2, and for a2 you know a0 by 2. So I just replace a2 by a0 by 2. So I am able to get a3 equal to a0 by 3 factorial. This is 2 into 3. right? So like that, like this, the solutions will arrive. So we have a naught, right? I am just uh, substituting the values of a naught, a1, a2, right, into the given solution, right, given the value of y, right? So here we have a naught, a1 is equal to a naught, and here we have a2 is equal to a naught by 2 factorial, and a3 equal to a naught by 3 factorial x cube. Like that it will goes on. So we have a naught in common. I will be taking a naught in from all the terms, and I am writing it as a naught 1 plus x square by 2 factorial plus x cube by 3 factorial, etc. So this is the solution, or this is the power series of exponential function. So I can write it as y of x is equal to a naught e power x, right? So here we have uh, some example problem, right? You can try to solve this, and uh, you can post your answer in the comment box, right? If you like this video, just like and share with your friends. It will be useful to you, and it will help you in your revision.